Hello, dear ones. You're all welcome to today's lecture. I believe you're all doing well. In our previous lecture, we looked at the effects of field excitation on the synchronous motor. Today, we are going to solve one example, then we see how we best understood our previous lecture. This is a question that we've already solved in our previous question that we solved. This time around, we are going to maintain the same power, output power, and then we vary the field current and we see what is going to happen. So let's look at the question again. We're saying that the 208 volts 415 kVA 0.8 power factor leading delta connected 60 Hz synchronous motor of the previous example, as I said, the previous example that we solved, is supplying a 15 horsepower load with an initial power factor of 0.8 power factor lagging. The field current IF at this condition is 4.0 amps. Okay, so we can see that they gave us the ratings of what the synchronous motor, and they gave us the rated power factor of the motor. So this 0.8 power factor leading here is the rated power factor of the motor. But at this particular point, at the situation whereby the motor is supplying a load of 15 horsepower, the power factor is what? 0.85 power factor lagging. So take note of that. So this is what we are going to use to solve our question. This is the rated power factor. But at this particular condition, with the field current of 4.0 amps, the power factor is 0.85 lagging. So this is what we're going to use to solve the question. Apart from this, every other parameter that we're going to use is what we had in our previous example: the windage losses, the synchronous reactance value, then the other losses. We are going to use the same values to solve this particular question. So let's see what the question demands from us. So A says that sketch the initial phasor diagram of this motor and find the values of IA and then the EA. So as we can see, we have to find this IA and then EA before we'll be able to draw a precise phasor diagram as we did in our previous example. So let's see. The question gave us supply load, okay, of 15 horsepower. So this is the output power, which is in the mechanical quantity 15 horsepower. So we have to convert this one to what, an electrical quantity of kilowatts. So we convert that one. We know that converting horsepower to kilowatt, we multiply by 0.746. All right, so we get it in kilowatts. But the question says that we should find the armature current. But we know that power P is equal to P in is equal to 3V phase cos, 3V phase IA cos theta. Okay, so if we make IA the subject, we will have it to be IA equal to P in over 3V phase cos theta. So if you are able to find our P in, you can just substitute, because we know this, we know the power factor also. We can substitute our values and find our IA, as simple as that. So let's see how we're going to find our P in, since we know our P output and we know the losses in our previous example, the same thing that we are using here, but the question hasn't changed. So we know that the P in is equal to P out plus losses. And what are the losses? We know that we neglected the RA. So if we neglect RA, our copper loss goes to 0. So the only losses remaining becomes the friction and windage losses, and then the core losses, which was given to us to be 1.5 and 1 respectively. So 15 multiplied by 0.746, which represents the power output, plus 1.5 plus 1 will give us 13.69 kilowatt as our input power. So knowing the input power, we can now substitute all our values into this particular formula, and then we find our IA. So our IA becomes 13.69 kilowatt over 3 multiplied by 208 volts multiplied by the power factor. Here, once again, we are using this particular power factor, the 0.85 lagging, because under this condition, the condition given, a field current of 4.5 with a load of 15 horsepower, the power factor of the motor is 0.85, but not 0.8 leading. Okay, take note of that. We are using this particular power factor, which is 0.85 lagging. So if you compute this, we are going to have the magnitude of our current to be 25.8 amps. Okay, 5.8 amps. So we have to represent this in a vector form. Okay, so we know the magnitude, so let with the angle, and we know that we're given the power factor, which is the 0.85. So we have to find our theta. Now we know that power factor is equal to what? Cos theta. So if you want theta, so we will get cos inverse of the power factor will give us the theta. You know all these things from our previous example, so there's no need for me to go into details. So we know that our theta in this case is going to be 31.8 degrees. So we can now represent this in a vector form, knowing the magnitude and in the angle. So our IA is going to be 25.8 angle negative 31.8, and you know the reason why negative, because it's a lagging power factor. A lagging means you have to indicate negative sign here. So we have our armature current under this condition. So the next thing that we need to find is our EA. Okay, so how do we find EA? Now we know our IA. We can go ahead and using Kirchhoff law to derive the formula from the equivalent circuit. We got our EA to be equal to V phase minus J XS IA minus IARA. But since RA is neglected, so that particular part becomes 0. So the only thing left becomes our V phase minus J XS IA. Now we know V phase, we know our XS, and we know our IA from the previous example. And once again, let me clarify this before we come to what we're doing here. Okay, here we're using what? V phase, but the question the value that we're given here is the line current, I mean the line voltage or terminal voltage, and we use the same thing as our phase voltage because the motor is delta connected, and a delta connection, the phase voltage and then the terminal voltage are the same. That's why we maintain the same 208. So take note of that. It's because of the delta connection. So we can go ahead to solve our question. Now our V phase, as we know, is 208 angle 0, because that is always our reference value, value. Okay, so minus J 2.5. Don't let this scare you, because it was stated in the previous question that our synchronous reactance is 2.5 ohms. So we are using that particular value. Multiplied by our current. The current, we had it to be 25.8 angle negative 31.8 amps. So if you compute this, we are going to get the EA to be 182 angle negative 17.5. Okay, and once again, the negative that we had here is because our in motor synchronous motors, the EA always lacks the V phase. So all the time the EA angle or the torque angle should be negative. Take note of that. So now we can go ahead and solve the question fully. For the question said we should draw the phasor diagram. So now we know our EA and our IA, so we can go and draw our phasor diagram. And drawing the phasor diagram, first of all, we need to draw our V phase first. Always take note of that. You draw your V phase first. So your V phase, okay, and then we know that the EA lacks this V phase by an angle of 17.5. So you draw the EA line, then it's lacks it by an angle of what? 17.5. So you indicate 17.5. That represents the EA. So that's what we have over here. So this is the V phase line, and this is the EA, and it lacks it by what? 17.5. And then this particular line represents the EA. So you write it 182 angle negative 17.5. Okay, now the question also said that the motor is what? Is operating at a lagging power factor, and then the current that we had to was lagging the V phase. So we come and draw the current line also. The current also lags the V phase by an angle theta. So this represents our IA. So that one too lags it by what? Angle of theta. So this is our IA. So that's why we also have over here. So our IA, vector IA is 25.8 angle negative 31.2. This 31.2 represents this particular angle theta. So as easy as that, if you are to draw the phasor diagram, then from there we draw our JXSIA line from the EA to V phase, and you know we can calculate for this particular value. We had it to be this multiplying by this, we had a 64 0.5 angle 58.2 volts. So you can write that particular value there also. Okay, so that's the first part of the question. So the second part of the question says that now if the motor flux is increased by 25%, sketch the new phasor diagram of the motor. What are the values of EA, IA, and the power factor of the motor now? So we can see that we are still maintaining the same input power, but this time around we are adjusting or increasing the field current by what? 25%. Okay, so that's what the question demands from us. So you can see that we are adjusting the field current. So we want to know the effects of the field current increase in the motor. All right, so take note of that. So let's go to the solution and see what we did over there. So we are increasing the field current by 25%. But we know that if we increase the flux by 25%, the flux is directly proportional to the EA. So the EA2 is going to increase by 25% from this particular formula. Okay, we know that EA is equal to K for omega. Omega is the speed of the synchronous motor, which is always constant. K2 is a constant value. Okay, so the flux is increasing by 25%, meaning that the EA2 is going to increase by 25%. So if initially we're having the magnitude of EA to be 1A2, it's going to increase by 25%. So increasing by 25% means that we multiply this particular value by 1.25, because it's increasing by 25%. So we add 25 to 100%. Then we having 125. So 125% it means that 1.25. Okay, so we are saying that our EA2, if we are relating to the EA1, so if the flux is increased by 25%, now our EA2 will be equal to 1.25 of the EA1, and we had the magnitude of EA1 to be 1A2, so we multiply by 1.25, and we'll get the new EA, the magnitude of new EA to be 227.5 volts. So take note of that. So this is our new EA value when the field current was increased by 25%. Okay, so to write this in a vector form, we can't use this particular angle, because whenever the EA, the magnitude of EA changes, the angle too should change, so that EA sine delta, EA1 sine delta should be equal to EA2 sine delta 2. So it means that the delta 2 value 2 should adjust itself. So how we need to go and find the EA, the delta 2. Okay, so we can say that in our previous discussion we said that EA1 sine delta 1 should be equal to EA2 sine delta 2, so that the power should always be, the supply power should be constant. Okay, in order for the supply power to be constant, this particular rule should be obeyed. So now we know the EA1 sine delta, we know the EA value, we know the delta value, and then we know the magnitude of EA2. The only unknown value is the delta 2, so we need to make the delta 2 the subject so that we find a new delta. Okay, so making the delta 2 the subject, we have it to be sine inverse of, that's if you make delta to the subject, to be sine inverse of EA1 sine delta all over EA2. Okay, so we know all these values. EA1 sine delta is what? The magnitude of EA1 is 1A2, and the delta value 2 is 175. So negative 175, sorry. So we put those particular values inside, and then the EA2 we had it to be 227.5. So if we compute, we are going to get our delta 2 to be negative 13.9. Okay, negative 13.9. You can see that the delta has decreased. Okay, from negative 17.5 to negative 13.9. So this is our new EA value. So we can write this in a vector form. We know the magnitude and we know the direction. Okay, so you can write in the vector form. That's the EA. All right, so now knowing the EA, knowing our V phase, we can go ahead and find our IA, because the question said that we should find the IA as well. So we go back to this particular formula because we know this now. We know this also. So the IA is the only unknown. So we can make IA the subject from this particular formula. And if you make the IA the subject, you are going to have it to be V phase minus EA2 over JXS. Okay, so if you substitute the values, V phase is 208 angle 0 volts minus EA2, we had it to be 227.5 angle negative 13.9 volts all over J 2.5. That's the synchronous reactance. So if you calculate this, we are going to get our IA to be equal to 22.5 angle 13.2. Okay, so here we can see that now our angle here is what, positive, so the power factor will be leading. If the angle was negative, it would have been lagging. But since we had a positive value or positive angle, it means that our power factor is now a leading power factor. So finally, the question said we should find a power factor. So we know that power factor is equal to what? Cos theta. Power factor is equal to cos theta. So theta is 13.2. So cos 13.2 give us 0.974 leading, because the sign here is positive. So we can go ahead and now draw our phasor diagram as the question demanded from us, that we should sketch the new phasor diagram. So this is how our new phasor diagram is going to be like. So first of all, we draw our V phase line as always. So we draw our V phase line, and it's 208 angle 0. That's the reference line. Okay, and we saw that the EA, okay, EA2 lacks the V phase by an angle of what? Negative 13.9. So you can see that we will draw the EA line, and then it lacks the V phase by an angle of delta. Delta is 13.9. Okay, so we write the value of the EA here too. And now the most important part is the IA. The IA now is leading the V phase. So here it will not come down here, but rather it's going to lead the V phase line. So it will be at this particular point with an angle of 13.2. So this is the angle 13.2 degrees. So we write the IA in the vector form. So 22.45 angle 13.2 amps. So this is the vector or the phasor diagram for this particular question. So that's all that the question demands from us. But let's see what we can deduce from this, because that's the most important thing that I want to put across. By the question, we are done. So we can see that when we draw the two phasor diagrams on this particular one phasor diagram, we can see that initially we had IA, and the corresponding internal generator voltage EA was 1A2 angle 17.5. Okay, so now when the field current increased, okay, by 25%, the flux increased by 25%, we saw that the EA also increased to this particular line, which was 227.5 angle negative 13.9. So you can see that as the flux increased, the internal generator voltage, or the EA, also increased from 1A2 to 227.5. Here the angle decreased from 17.5 to 13.9, because we want this line, okay, to this particular line, and then this here to this particular line to be equal. So if you find the EA, okay, we'll come to that, so you just hold on. Okay, so we can also make one deduction from it. So you see that when it was operating at a lagging power factor, we saw that the EA was less than the V phase. The EA was what? 182, and the V phase was what? 208. So the EA was less than this, because we said that at the lagging condition, the synchronous motor is under excited, and the under excited condition, the EA is always less than the V phase. And then when we over excite it, it will operate in the leading power factor condition, and at that particular condition, the EA tends to be greater than the V phase. So that is all that we want to put across. So we saw that. So also, let's see another constraint that we set in our previous slide. We said that at every instant, the EA sine delta should be equal. So EA sine delta 1 should be equal to EA 2 sine delta 2. And let's see if we can prove that particular point. So let's take the value EA1 and then its delta value and compute. So EA1 is 182 sine 17.5 and we had 54.72. Also, when we took EA2 sine delta 2 and EA2 was what 227.5 sine 13.91, we had 54.69, almost the same. Okay, 54.72, 54.67. The difference came as a result of the fraction, the decimal points that we use over here. We approximated the values. Other than that, they would have been the same. Okay, it's because if you draw a line from here to this particular point, it should be equal to the line from here. The line from here, this particular point. Okay, because the power hasn't changed. If the power hasn't changed, so it means that this particular value should be the same, so that the power will maintain the same. I explained this using the power formulas in the previous slide. Also, let's look at another point too. We set another condition that IA cos theta should always be constant too. Okay, so IA1 cos theta should be equal to IA2 cos theta 2. So let's see. IA2 was 25.8 cos 31.8 and we had 21.927. IA2 cos theta 2 was what? 22.45 cos 13.2 and that one too we had 21.85 85 amps. Okay, if we are to approximate everything to one decimal place, they will all be 21.9, 21.9. Okay, so you can see that these particular values are the same. Okay, because of the decimals that we use, that's why we didn't get the same value. But if you had to use all the decimal values, they would have been the same. Ideally, they should be the same. So we can say that the horizontal line from the IA1 to this point and then this point should always be the same because the power hasn't changed. So they should all be the same. That's why the values that we are having here are all the same. Once again, this part is not part of the question. This was just to analyze the answers that we had and then go on. So that's all for today. Till we meet again, this is Akanyele Bismarck. I say stay safe. Goodbye.